Then I do this more. It's also very satisfying when you click it and it crosses it out. Yeah. So I thought what it was it had to have two different do it or so I guess we'll get accountable. Yeah, that's fine too.
Oh, okay. Okay, it can. I don't know. I guess maybe because I need some heat up, but I heat up for half an hour, so anyway. Because I was thinking I may just write on the whiteboard, but we don't need that. Let me have this. Okay. Yeah, I plan to talk about this, so I can write this equation on the whiteboard. But we don't need this. Okay. So let's get started. So today is lecture 3, and today we are going to talk about statistics and data analysis. And here I listed 6 points. So for the first one, when we have the data, we need to report the data. So we are going to go through the significant figures and use of Excel. And then when we have data, we know that data has errors. So we need also to describe the uncertainty. So I will go through something about error, uncertainty, accuracy, and precision. Then we know that when we have the data that with uncertainty, it can be propagated through the functional relations. So we are talking about error propagation equations. Also, we have the data. We also have a question like, what's the significant? Are the different significant? Like how to compare the two samples. So I will talk about t-test. Also, when we have the data, when we have the outliers. So we are also going to talk about how to identify the outliers. And finally, we want to find the functional relation, especially for the linear functional relation between two variables. So I will talk about linear regression. So first, let's look at, let me just make sure it's recording. Okay, so for the significant figure, as we discussed in the first lecture, so basically significant figure, like they are the digits. And the definition is not quite important, but the rules are important. So let's look at the first rule. For the non-zero digits, they are always significant. So for this one, it has 4 significant figures. And for the second one, like any zero between 2 significant digits, they are significant. So for this one, it has 6 significant figures. And for the third one, we have a 0 at the very beginning, but this 0 does not count. So for this one, we only have 3 significant figures. And for this one, again, we have so many zeros in the front of the non-zero number, and these zeros are not significant. So still, we only have 3 significant figures. And for the fifth one, we have the 0 at the beginning, and we have 0 as end. In this case, this 0 counts. This 0 does not count. So we have 1, 2, 3, 4. We have 4 significant figures. And for the last one, we use the scientific notation. So we don't care about this. We only care about this one. And for this one, we have 3 significant figures. So do you guys have any questions in terms of rules? Okay. This is important because we are going to report data. And this shows the example of the lab report from previous students. And we can see the first one, it is clean and brief. But on the other hand, on the right side, we can see that it has the significance. This is only 1, and this is 3, this is 2, and this is a lot. So this is bad. So in your guys' assignment, because we don't have lab report, so in the assignment, we should try to make sure the significant figures are consistent. And these rules also apply to other lab reports from other courses. Yeah, add some animation. And then I also want to talk about working with tables, because I assume most of you guys use Excel to make the table, and then we copy and paste it into Word and PowerPoint. So I will make an independent video to talk about how to specify significant figures and the addition of the tables and the movements from the table to Word file. Because sometimes when we do the movement, the format will change, will look not that good. Then I'm going to talk about how to quantify errors of my data. So there are 2 concepts. For the first one, the measurement error, it refers to the measured quantity value minus a reference value. So the measurement error equals to x minus x prime. So this one is the reference value or the true value, and this one is our measured value. And for the uncertainty of the measurement, it is a non-negative parameter characterizing the dispersion of the quantity values being attributed to a measurement based on the information used. I think this definition is a little bit intuitive. So basically, when we have data, we have an arrow. So this is one arrow. But if we have a bunch of data, we will have a bunch of arrows. So uncertainty is kind of like we are doing statistics on these lots of arrows. So we use a statistical method to describe the arrow, and this is uncertainty. Okay. And then I want to talk about the source of errors. So basically, we have 4 sources. The first one is observer. We know that different people may have different readings, especially for the colon or for the pipette. The next one is about the method. For example, we are doing the titration. But the chemical reaction may not be complete. Like the chemical reaction may only goes to 98%, but it will take forever to be 100%. But we cannot wait forever. So we may only use this one. And this is so the error will be introduced by this. And the third one is instrument, because the instrument may not be able to give the true value because of some white noise or some problems with the instrument. And the fourth one is object to be measured. And here is an example. This picture shows the DDT concentration in a field. And if we are interested about the average concentration, like this one, on this site, because of the budget, we can only take limited number of samples, like here, here, here. Anyway, so based on this sample, we can calculate the average concentration. But we can imagine that they are different from the true concentration. Maybe by chance. Oh, it's just opened. I mean, this is opened 5 minutes ago. I don't know why.
Oh, okay. Do you need anything else? Or?
I think that's it.
Okay.
Thank you. So and this is due to the heterogeneity of this sample. So the object itself can introduce error. And then I also want to talk about the types of error. So basically, we have three types of error: random error, systematic error, and gross error. And random error refers to data scattered approximately symmetric about a mean value, and it will affect precision. And I will talk about precision in the next slide. And we can deal with it statistically. So basically, we can assume this eta is a random error, and this random error usually can be assumed to be follow a normal distribution. So, and around 0. And this is its variance or standard deviation. And we usually assume that this is infinite. This is not infinite, and this is greater than 0. So we can use a normal distribution to describe random error. And for the systematic error, it refers to the reading too high or too low, and it will affect accuracy. For example, if this is our measured data, and assume this is a true TIU, this is a true data, and ideally we will have this curve. So this is 1:1 ratio line. So ideally, our measurement should be something like this. But for the systematic error, it could be something like this. So the measured value are consistently lower than true value. Or maybe it can be something like this. So if the value is very high, the measured value will be consistently smaller than true value. But if the value is very large, then the measured value will be consistently smaller than true value. So in this case, for the systematic error, sometimes we use a linear regression to fix this problem. The last one is gross error, and it's usually relatively obvious. And sometimes we call that outliers. And it is detectable by carrying out sufficient replicate measurements. So if we only have one measurement, that measurement may not be reliable. And here shows the statistical test suggested by US EPA. In this class, we are not going to conduct this test, but I just want to let you guys know, if we want to figure out the outlier officially or scientifically, we can find this guidance and to conduct this test. So far, do you guys have any questions? No? Okay. The next one is about accuracy and precision. So for accuracy, it refers to the measurements of agreement between measured value and the true value. But the true value is sometimes unknown. So if we want to know this true value, or if we want to pretend we know the true value, we can do some tricks. And I will talk about this in the organic chemistry unit. So we will revisit this part. Here are the measures of accuracy. So we have the absolute error, which is defined as our measurement minus the true value. And we also have the relative error. So we use the absolute error divided by the true value and times the 100%. And so geometrically, accuracy refers to the distance between the mean of the measurement and the reference value, or the true value. And the next is about precision. So precision relates to the reproducibility of the results, like how similar the values obtained in exactly the same way. So in this plot, the precision reflects to the whiteness of this normal distribution. And to quantify precision, we usually have two methods. The first one is absolute difference. The second one is standard deviation. But I think in our daytime experience, I think the standard deviation is more commonly used. So my question is, do you guys think why standard deviation is more commonly used than this one? Do you guys have any ideas or any guess? Or taking notes? Like why this is more commonly used? Oh, I will upload these slides on Canvas, so I think for some of the details you may just look at the uploaded slide, maybe. So any of you have any guesses? You?
I suppose, I'm not sure if I'm reading absolute difference wrong, but I suppose that because we can always find the sample mean, it's a little bit easier to develop, like to know, like, hey, I have a sample mean.
Yeah, that should be.
That's also a sample mean.
Yeah, I
Okay,
think that's a
never mind.
display error.
Let me correct my notes.
But let's go try. So basically, as far as I know, one of the reasons is that because this is absolute value, we can say if we have an absolute value, it will be something like this. But this is quadratic, so it will be something like this. So this function is not, if we take the differential of this function, we will have two. We will split it into two parts. But if we take the deviation of this one, it is continuous. So basically, in the mathematical statistics, we want to find like the maximum value of the precision, or we want to minimize the precision. So if we want to do this, we can just take the differentiate of like the sample size or the mean. And this is more convenient to optimize by using standard deviation instead of absolute difference. So I think this is one of the reasons. Anyway, so we have precision and accuracy. And so basically we have four combinations. The first one, we have low accuracy and low precision, which is bad, and we don't want that. And we also have the combination of high accuracy and high precision. And this is a goal that we always want to purchase. But because it is relatively expensive, we want to chase it, but sometimes we cannot get it. So what we have are these two situations: high accuracy but low precision, and low accuracy with high precision. So between these two, do you guys think which one is better? You?
High accuracy, low precision, because it would get you closer to the actual mean of the data.
This one? Mm-hmm. Yeah. Any other have ideas? Yes, yeah, that's it. Because with high accuracy and low precision, although we have very low precision and the data are scattered, but we can just increase the sample size and calculate the mean, and then we can make sure, and then we are sure that our mean are very close to the true value. But for this one, we also need to measure the difference between these two. And so in the lab, I think you guys have already met this autopipette before. And I think this photo was taken many years ago, and they look very new. And actually, when I see this photo, I was thinking like age should be the intensive property. And for the autopipette, it has its accuracy and precision. So in your calculation in assignment 2, you may use these values. We also, like for the volumetric flux, they also have accuracy and precision. And this only provides the precision. So when we measure the volumes, we cannot get the very perfect volume of this. So we may have some errors. The same for the balance. And again, we also have the measurement error. But in our calculation, we simplify this process because it's very inconvenient for us to go to the lab and find the accuracy and the precision. So in the assignment, that's the answer. Okay, this one. Yeah, so in the appendix, so this is assignment 2, but please note that this is an independent module. And at the end of this assignment, we have a summary of the instrument errors here. So when you guys are doing the calculations, you guys can refer to this table. So far, do you guys have any questions? No? Okay. So, because we know we have the errors, and during the calculation, we may have some functional relationships between two variables. For example, we want to calculate the concentration. But the concentration we know equals to the mass divided by volume. And we can also consider this as the concentration is a function of volume like this, and the curve is something like this. So let's just say our volume have some errors. Like let's just say this is x refers to the volume, and the delta x refers to the error of that volume. And and we can assume they equals to each other. So during this functional transformation, we can see that the y, let's just say y equals to 1 over x. And we can see that we have delta y2 and delta y1. Based on this functional relationship, delta y2 does not equal to delta y1, which makes it's complicated because we can assume this is a normal distribution, but after transformation, it will be a skewed distribution, which is harder to handle. So in this case, we can assume the errors of x is relatively small, and this is the case for most of the instruments. And if we assume like this, we can deal with this like we can create a curve. We know that for this straight line, if we do the projection or the transformation, delta y1 equals to delta y2 in this case. And the slope of this straight line equals to the tangent of this point. And then we can have this relation, delta y1 equals to delta y2. And we can just let it to be delta y. And according to the geometric relation, delta y equals to this one. So we can simplify the nonlinear problem into a linear problem. And here shows the deviation of the error propagation equation because error propagates through these functional relations. But I'm not going to talk about them in details because it is out of the range of this class. But I want to say that in our practice, we have this. like y equals to x1, x2, and xn. Again, the concentration is a function of mass and volume. So it equals to this. And this is just the general form. And after some deviation, finally we got this one. I don't know why this has a shift, but so we just need to know this one. So this one tells us that the arrow of y, and then we take square, equals to the sum of the arrow of x times the partial differential of y to x squared. So basically this is the sum, and this is the sum of square. But for each of the components, the arrow from the component, we should times the slope of itself, and then we make the sum. I think this is one of the beautifulness of the math, because even though these are very complicated, but finally we can get this brief expression. And by having this expression, we can calculate any arrows from any transformation. Oops. And here are some three examples. And these three examples are the functional relations that we frequently use in our daily life or in our lab. The first one is summation and subtraction. The second one is division, and the third one is multiplication. And for the summation, suppose we want to transfer the volume of like the sample. We may transfer it for the first time and then transfer it for the second time. Or if we want to transfer some wastewater samples, we add some volume of the wastewater sample and then we dilute it. So we want to know the uncertainty of the total volume. And this is a general form of this summation. And again, we can calculate the partial differential of y to xi, and then we can calculate delta y. And then delta y equals to this. But to be more simple, if we assume y equals to x1 plus x2, and then the delta y squared equals to delta x1 squared plus delta x2 squared. So in other words, the absolute error of y, when we, so we don't have square here, equals to the sum of each component, equals to the sum of square of each component, and then we take the square root. And then for the division, again, the general form is like this. And we can calculate the partial differentials. And finally, we can get y equals to this one. But this one looks not intuitive. We can transfer it into this one. So in this equation, we can see that the absolute value divided by the true value, which represents what? We use absolute error divided by the true value. It represents to the relative error, right? So in this equation, the square of the relative error of y equals to the sum of the square of the relative errors of each component. And the same for the multiplication. We can see that after deviation, they are the same. So no matter we do division or multiplication, the error propagation relations are the same. And on the other hand, it is not related to A, B. So, and for the division, like for example, again, we have the concentration equals to the mass divided by volume. And for the multiplication, we have the mass equals to the concentration times volume. So far, do you guys have any questions? Okay. So we don't need to derive this, but we need to know how to use these error propagation equations. And on canvas, I uploaded a paper like here, and in this paper it provides the table of error propagation equations, and it summarizes almost all of the functional relations between x and y. And here is an example. So do you guys want me to go through this example today or on Thursday? Or I guess I will go through this example on Thursday, and I will continue to other knowledges of today. So the next one is about significant difference. Like if we have two sets of samples, and I don't know why this doesn't show, but we can say this is x bar, and this is x2 bar. So we can have two sets of samples, and we have its mean, standard deviation, and sample size. So we know these three pieces of information. And the question is, are they significantly different? And so we can compare this by using t-test. And the full name of this t-test is called two-tailed t-test for independent means with equal variance. But in this class, we just call it t-test. But we should know that we may have one tail and for independent means and with unequal variance. So we have different combinations. And there are several ways to conduct a t-test. And here I choose the way that I think is the most intuitive one. So we want to answer the question, if 0 belongs to this range, and this range is called confidence interval. And note that this should be x bar and x2 bar. And note that this is plus and minus. So we will have a range. So this is lower range, and this is upper range. And then we can do the calculation in this part. And here, S is the weighted average of S1 and S2. And N refers to the total degree of freedom. And if we have two sets of sample, the degree of freedom equals to the total sample size minus 2. And the alpha here is a significance level. And usually we take this as 0.05. So basically, we can have a range like this one. And if 0 is inside this confidence interval, then there is no significant difference. And if 0 is outside the confidence interval, then there is significant difference. And on the right side, I just show some intuitive images to show why this happened. So basically, if we have sample, we know that the x, we can assume it follows a normal distribution. And another sample can be also assumed to follow a normal distribution. And then we know that the mean follows a t-distribution from statistical class. And also, our question is if mu1 equals to mu2, or if they are not. And this question can be transformed into another question like, if the difference equals to 0, or if the difference does not equals to 0. And we know that if we want to make the difference can also be expressed as a t-distribution, because we have two t-distribution here. And this t-distribution can be calculated from the normal distribution. So basically, the distribution of D can be calculated by the information of these two samples. And then we can construct the confidence interval of this D. And if 0 is inside this confidence interval, then there is no significant difference. And if 0 is outside this confidence interval, then there is significant difference. So this can derive this one. And here is also another example. I think I can just go through this example. So first we have two sets of data here, and based on the data, we can calculate its mean and the standard deviation. And then we want to calculate if 0 belongs to this range. And in this range, for the n, we can calculate by n1 and n2. This is this value. And for s, it is the weighted average, and the sample size are equal. So it's just to the half of the sum of these two components, and s equals to this one. But the important thing is t. T refers to the t distribution with degree of freedom with 18, like here, and the alpha equals to 0.05. And the t value can be found by the t table, like shown here. So we have alpha equals to 0.05, and the degree of freedom equals to 18. So we can find this value here. So by having the t value equals to this one, we can calculate the range, and the range shows here. And we can see that 0 does not belong to this range. So our conclusion is that they are significantly different, and we need to specify p is smaller than this value, or we can specify alpha equals to 0.05. Like these two are equivalent. So for this one, do you guys have any questions? Okay. The next one is how to identify outliers to my data. So suppose we have some measurements from the sample, and we have our sample like x1, x2, all the way to xn. And the question is, are there potential outliers in the data set? Here I just add the potential here because, as I mentioned before, if we want to formally identify the outlier, we need to do statistical test. But in this class, we can just say the potential layer as outlier. So we can use the box plot method to identify the potential outlier, and we can consider it as the statistical outlier. But in future, when you guys are doing work or doing research, you may need to use the statistical test to identify the outlier. And so here shows the box plot. So based on the data, we can calculate the maximum value, the minimum value, and the median of upper half, the median of the whole data, and the median of the lower half. By having all of these values, we can calculate this interquartile range, which equals to Q3 minus Q1. And by having this value, we can also calculate the upper fence and the lower fence. And the upper fence equals to the median times 1.5 times IQR. And the lower fence equals to Q1 minus 1.5 IQR. So we will have another range from upper fence to lower fence. And then we can see if our sample does not inside this range, like if the sample is here, then this sample is considered as an outlier. And here is an example. So suppose we have the, this is not sodium. Yeah, sodium concentration in a solution, like shown here. And in this data, I just order it from small to large because we want to know the median. So first, when we got the data, we need to rearrange the data like from small to large. And based on the data, we can see Q3 refers to the median. And so we can say the median should be here. So it is, Q2 is a median. So it is the average of these two. And for Q1, this is the median of the lower half. So this is Q1. And for Q3, this is the median of the upper half. So this is Q3. So we have Q1, Q2, and Q3. It's ready to calculate IQR, and this is equals to 8. And then we can calculate the upper fence and lower fence. And in this case, this is the upper fence and this is the lower fence. And then we can have this range. And we can check, like this one is outside of this range, and this one is inside. So 56 is an outlier or potential outlier. And for here, it's okay for this class. But in future, when you guys are working, your conclusion will be further statistical test is needed. So far, do you guys have any questions? No? Okay. The last one is linear regression, because we want to know the functional relation between two variables. And for the linear regression, I think we have, most of you guys may learn it in the statistical class. So the y equals to a plus b times the independent variable plus a eta I. This should be eta, like this one. And so x and y has the linear relations. And the eta here is the error term. And it's usually assumed to follow a normal distribution, because we know that if we have a regression line, but the data could not be perfectly stand on the line. So the distance here refers to the arrow. And usually we assume this arrow follows a normal distribution, like here, with the mean equals to 0. And here shows an example. Suppose we have the x and the y data, and by using Excel, we can construct this plot, which I will show in the recorded video. And then we can use Excel to automatically generate this linear regression function. So this step is relatively simple, because we only need to play with the computer. But we have some other questions. What about the uncertainty of A and B? And and given we have a new data X, we know that we can do the calculation by plug this value into this equation, and we can know the prediction of Y. But our question would be, what's the uncertainty of this predicted value? Because uncertainty is important. So to answer this question, we need to go through some of the steps to get the answer. And we can see that there are so many terms and so many things we need to do the calculation. And when I first see this, I was like this. But it looks complicated, but we can just write it into Excel, and we can use the Excel to do the calculation. And here is an example, and I use different colors to specify different steps, and I also use the arrows to show each step. And because of the time, I think I will go through this on Thursday. So by having one Excel sheet, we can just copy and paste the data from homework, and then we can get the results automatically. So I will discuss this on Thursday. And for the lecture summary, I think I will also go with you guys on Thursday. And here's the ending notes. So on Wednesday, we are going to have lab 2 to prepare the Flint kit. And I also want to emphasize that assignment 1 and assignment 2, they are due on next week.
I have a question about
Yes.
that. Assignment 1, there's only a place to like do the reflection, to like submit the reflection. Are we just submitting the reflection?
Yes,
Because
that's
the solutions are
self-evaluation.
posted?
Yeah, solution is posted.
Okay.
Yeah, I think the solution is posted at the end of the page.
Yeah, I just didn't know if that was on purpose or not.
Yeah. If you guys cannot find solutions, then let me know. But these 2 assignments are all due on next week. And assignment 2 is the statistics. And quiz 0, quiz 1, and quiz 2, they are also due by next week. And then on this Thursday, I think as we discussed before, we will have QA, but we are going to do the in-person. So I will send an announcement. And I will revise the ELMS page. And as I mentioned, the plan is to go through some of the common questions and answer questions. And if you guys don't have questions, you guys may leave. Okay, so that's it.